today I'm going to discuss the physical chemistry unit 5, which is chemical kinetics. Uh, what is chemical kinetics? It is the study of the rate of chemical reaction, that is known as chemical kinetics. So we are going to study the reaction rate, at what rate the reaction is taking place, like different reactions like uh, parallel reaction, reversible reaction, etc. So in this unit, we are going to discuss the differentiation between the order of and stoichiometry of the given reaction. This is the first objective of this unit. So we are going to calculate the order of reaction with respect to species involved in the given reaction, and we are going to calculate the total order of the given reaction, and we are going to find the expression for zero order, first order and second order reaction, and we are going to determine the order of the reaction experimentally. These are the main objectives of this unit. So chemical kinetics deals with the study of changes in the properties like concentration, pressure, density, weight, etc. with respect to time during the chemical reaction, or it is the study of the rate of chemical reaction. So some of the important, the next topic, we are going to see some of the important ends of kinetical study. To know the mechanism of unknown reaction, where we are going to calculate to see the mechanism of the unknown reaction. Further, we are going to calculate the thermodynamic parameters, what we have studied in the previous units, like delta H, delta S, delta V, delta G of the reaction, and to know the corrosion of the different materials. Finally, here also, and next point is kinetics of photodegradation of industrial waste. Photodegradation is nothing but the absorption of photons. So next is pharmacokinetics, to understand the property of new drug molecule and its interaction with the living cell. We are going to study the drugability properties, how the drug interacts and the rate of dissolution. We are going to study with the chemical kinetics. And kinetica of polymerization, to know the good quality of the plastic and rubber, etc. And some more important properties are there. Go through that. And last one is, this one is also very much important, enzyme kinetics, to know the drug protein binding. You are going to identify the drug interaction with the protein. Protein is nothing but the amino acids. It is having the interaction with the drug molecule. So, and also drug and DNA binding interaction. Using chemical kinetics, we are going to identify the binding interaction. And these are the terms important for this today. And next, coming to the topic, here basic concepts like what is homogeneous reaction, what is heterogeneous reaction. Homogeneous reaction is the system which exists only in one phase. The reaction takes place in only one phase. So heterogeneous is having more than one phase. The reaction takes place one or two system, two, three systems. So this is known as heterogeneous reaction. So next topic is molecularity and stoichiometry of the reaction. Here molecularity is the number of molecules that come together to react in a single step reaction, that is known as molecularity. And stoichiometry is stoichiometry equation. Your in practical, some of the stoichiometry equation we have derived written. So stoichiometry equation represents the number of moles in the different reactant or species or molecules taken part for the reaction. This is known as stoichiometry. So stoichiometry equation represent number of moles of different reactant taking place at the reactant. So here some one example is given. 2a plus 3b plus 2c is gives rise to product where 2 represent the moles and the uh, of product reactant A, and 3 represent the moles of reactant B, and C 2 represents the mole of reactant C. Here if you add totally it will be 2 plus 3 plus 2 5 7 moles of different reactant. 7 moles represent this documentary and more reactant. It represent the molecularity part of the reaction. This is the difference between molecularity and stoichiometry of the reaction. So the first major topic is here is molecularity of the reaction. Here you are going to identify the number of react species. How many numbers of species? You are not going to concentrate on the number of moles. Here molecularity of the reaction represent number of species taking in the reaction. So here A plus B gives rise to X. Further in the K1 is nothing but the rate constant that is we are going to study in chemical kinetics. X and further X plus B in the rate constant of K2 gives the product X1, where X1 plus C gives to X double X X2 with the reaction reaction rate or rate constant which is K2, and X2 plus B gives X3, and X3 plus A gives for X4. This is what the reaction taking place. This is taken as an example where one step is X1 plus C in the rate constant K2 gives X2, which is in the slow step. We are going to identify the rate of reaction here. When we are taking two species like X and C are involved in this reaction, so this is bimolecular reaction. For example, here they are given C. Yes, here we are taken C bromomethane with hydroxide gives methanol plus bromine. This is bimolecular reaction. Two molecules we are taking. So this is bimolecular reaction. And the next, yes, here we are taken three molecules giving product A plus B plus C. A plus C gives X, X plus B gives X bar. This taken as an example to know the reaction for different types of reaction. So X bar further gives at the rate of reaction or rate constant K3 gives the product. Here, this is the only species involved here. X is the further This is unimolecular. What we can say? This is unimolecular reaction. Only one molecule is giving rise to the product. This is known as unimolecular reaction. Uh, and next topic is molecularity of the reaction, whether it may be one, two, or three molecules giving to the product. This is known as bimolecular reaction. Whether it may be up to three molecules taking place in the reaction is known as bimolecular reaction. Here it may be A and B, which is having the coordinate and getting, and further the molecule may be having up to three molecules where the reaction taking place is known as bimolecular reaction. For example, A and B, this for two molecules A and B and C, this for three molecules where reaction is taking place, and molecularity of the reaction cannot be greater than 3. For example, if it is greater than 3, here A, B, C, D, it is having 4 molecules different. The reaction may not have interaction with the A and D or B and C. So in bimolecular reaction, then 4 molecules cannot take will not be there. Only 1, 2, or 3 molecules is known as for bimolecular reaction. And further in the next topic, we are going to discuss about rate of reaction and rate constant. When, for example, rate of reaction uh, is nothing but the rate of disappearance of reactant or rate of formation of the product, where the reactant get disappeared and the formation of the product is formed. Here we are going to study the rate constant of the reaction. See, A giving rise to the product with rate constant K. This is the K, where this known as the rate constant. This is nothing but the rate of reaction is equal to rate of disappearance of A or rate of formation of the product. It can be written. So taking differentiation on minus d by dt into A. A is the reactant, or it can be written as d into dt, d by dt into B. This is the product. Where further in the next step, it can be when it is in the equilibrium, the reaction it can be written as minus d by dt into A is equal to d by dt of B. Reactant and product is equal to product, or d by dt into A or d by dt into B alpha a to the power of n, where A is this big A is known as amount of A. The amount of this in this reaction, the amount of A is transferred to B. This amount, this denoted here, where n is the order of the reaction. So this n denotes the order of the reaction. And further it can be written as rate is equal to K into A to the power of n, and K is the rate constant, this value. And further rate constant K is equal to rate of reaction. So it may be K can be denoted as rate of reaction or rate constant, it can be denoted. So In the next example, you get to see here A plus B gives the product where K is the rate constant or rate of reaction. So it can be written as K into A to the power of N and B to power of M. N and M represents here. A is the reactant and B is also another reactant where N is the order of reaction of A and B is the M is the order of reaction B. So, for example, in this step, here we are taking what C2H5OH. We are taking ethanol and with the potassium, 2 moles of potassium permanganate, giving the product. What is the product we'll get? You may get here CH3CHO. One is acetaldehyde and 2 moles of manganese oxide and 2 moles of potassium means OH here. This KOH plus 2 moles of H2O. This is the reaction taking place, and the rate of reaction or the rate constant is, you can write for this example, it can be written as to identify the rate of reaction or rate constant. K1 is the rate constant. K1 into ethanol into potassium permanganate of order of reaction. This is the rate of reaction we are going to calculate. And further, to next topic is to determine the order of reaction. Here the important role is to study the reaction kinetics. See here. The order of reaction plays a very important role in the study of the reaction kinetics. So, for example, if you take here A1 gives the product B with if you're going to calculate the rate constant K into this one K into reactant. How much moles of reactant taken here? A1, this is the rate constant or rate of reaction. And if you are taking two different uh, molecules here, A1 plus B gives the product where it can be written as K into A1 into B1. This K is the rate constant into reactant A1 plus B. This you are going to identify the rate constant or rate of reaction. Or and when you are taking three different molecules, you can be written as K into A1 into A2 and C to the power of half. Why we are taking here? This is for the while you are taking three molecules, giving the product. To identify the rate of reaction, we are going to calculate AK into A1, B into 2, B to the power of B2, and C to the power of half. This one is known as the rate of reaction for three molecules, three different molecules. You are going to calculate like this. And further, the A2 in plus B of for Kc. This can be written as rate K into A2 by this one minus half is there, so we are taking in the denominator, so we are going to write B to the power of half. So this in the next we are going to Next topic we are going integrate. Yes. Integrated expressions for zero order, first order, and second order rate constant. We are going to calculate here for three different order of reaction. We are going to calculate the integrated expressions. So for zero order reaction, A gives to the product where with respect to K naught, this is the rate constant. K naught is the zero order or rate constant. It can be denoted where further it can be written as rate is equal to dx by dt alpha 0 uh, 0 to t. Why you have taken A here? A is nothing but the amount of x moles. Yeah, amount of A transferred to the product. How much amount it is converted into the product. We are going to take in it as x here. X is the amount of A converted to the product. Uh, T is with respect to time. At what time the rate of reaction is taking place. So K is the rate constant. Further, we are going to write dx by dt is equal to k naught a minus x naught or is equal to k naught. On integrating, we can write further it as x is equal to this dx by dt is equal to k naught into a minus x naught can be written as in integrating x is equal to k naught into t. So further in the equation 2, see this is the plot what we have obtained for this reaction. Here x is the amount which this x is the amount which A is converted into product, the amount. T is nothing but the time taken for the conversion. So we will be getting this plot where this is known as K naught. This is the rate constant. The amount where it is converted to the product is shown in the is the X is the symbol it is shown where X denotes the amount which transferred to the product where A is converted into the product is noted as X, and with respect to time we are going to get the rate constant from this plot. So next, so further we can also calculate the half life for the zero order reaction. What is the half life time? It is the half of the reaction. So here what we have got, x is equal to k naught into t. So k naught is nothing but the from this plot. This is the k naught rate constant into t. You are going to get the zero order reaction. T is nothing but the time. So to calculate the half life time for the reaction, T half it is given by T half is equal to A by 2k naught. See, A is nothing but the what A it is. A is C here. This A, what you are seeing here, it is nothing but the initial concentration of the reactant. Initial concentration of the reactant is this A. This A is the reactant here. One second, a lot of people are asking for the acceptance. Yes. The A is the reactant, where small a denotes what we are taken here. The small a denotes the initial concentration of the A. So 2K naught, how you got 2K naught here? This K naught is the rate constant of that reaction. Well, coming to the next topic is the first order reaction. In the first order reaction, A gives rise to the product with rate constant K1, or the rate of reaction dx by dt alpha A minus x, where d further in differentiating we can written as dx by dt is equal to K1 into A minus x. This is the equation. On integrating, we'll get log of A by A minus x is equal to K1 into t, the time, by 2.303, where further it can be written for K1 coming on the left hand side, taken in the left hand side, K1 is equal to 2.303 into t, log of this one, log of A into A minus x can be written on the right hand side into log of A minus A by A minus x. This is the equation 5. Further, plotting the graph for this equation, this is the log A by A minus x. This is the initial concentration of the product reactant A. So with respect to time, we are going to plot this graph. This is the K1, where K1 is the rate constant. This is known as the rate constant of this reaction. So rate constant of this reaction is K1 2.303 into slope. This slope, what we are getting, the slope value, how we are going to calculate A. This one, if you take A, B, and C, AB by BC, you will get the slope value. Slope value into 2.303. That is the K1. This is what they are given here. See, to calculate slope, K1 by 2.303. So for this reaction, you are going to time the half-life time for this reaction is T off is equal to 0.693 by K1. This is the half-life time for this first order reaction. And for the second order, here we are taking to A plus B gives to the product, where with respect to K2, this is the rate constant. We are taking this example here, where it can be rate of reaction can be written as d by dx by dt alpha into A minus x. This the initial concentration. A is nothing but the initial concentration of the A, and B minus x. B is the initial concentration of the reactant B. This is the initial concentration B. The small b denotes the initial concentration of the reactant B, and x is nothing but the amount of A or B is transferred to the product. How much the after taking the reaction taking place, how much the amount of uh, product is formed is. So further here in the next step, it can be written as dx by dt alpha into A minus x into B minus x, where B small b denotes the initial concentration of the reactant B, and with respect to the first order reaction is not equal to B. So K2 from the first order, what we are taken, K2 is equal to 2.303 by time B minus A. B minus A is nothing but the initial concentration of the B and initial concentration of A, ln of A into B minus X divided by B into A minus X. What this from the rate of reaction. we're going to derive this equation 7. Further on, see here, yes, in this step where a is where k2 is equal to 1 by t into x by a minus x. This is the rate of reaction for the second order. So from x by a minus a into a minus x versus t, we are going to plot this graph. This is t, nothing but the time with the concentration of second order. This is the concentration of the A and B. So we are going to get this rate constant where it can be denoted as K2. At what rate the reaction is taking place, we are going to get, as this is the concentration with respect to time. And further from this, what we can write, 1 by a minus x is equal to 1 by a. We're taking a on the right hand side plus concentration K2. This is the rate constant of the reaction of this reaction. So K2 into T. This is the equation 9 what we have got. Further plotting the for first order, here we can also calculate 1 by a minus x. Here two reactants are there, A and B. So we are going to calculate for the first one also. 1 by a minus x with respect to t. This is the time, and this the, with keeping a as constant, we are going to calculate for the B reactant also, the rate of reaction. So here this one is also K2, and this is the 1 by a, and the slope can be written as K2. K2 is nothing but the order of rate constant or rate constant. This plot. Further, for this we can half lifetime is T of is equal to 1 by K2 into A. This is the equation 10. We are getting this equation from the equation 9. Half of this equation, see, T of T of T of half lifetime of the reaction is 1 by K2. And further, in the next, for a half order reaction is nothing but the reaction. For example, if you take it in this example, we are going to know here we are taking N2O5 dinitrogen peroxide. You see, for this example, is converted into nitrogen dioxide plus oxygen. So we cannot write O1. So see here where we are writing of oxygen. So in this reaction, you are going to see this is nothing but the first order reaction, but some of the reaction we cannot write first order. So it takes place half order reaction. The reaction itself taking place the half order reaction. So it is denoted by half oxygen. It's nothing but the 1 mole of oxygen. So this is the half order reaction. So this is the tabular column for zero order, first order, and second order. This is the rate expression and concentration time relationship, and this is the half-life time for that, and this is the linear plots what we have observed, x versus t and log a by a minus x versus t and 1 by a minus x versus t to identify the this plot. From these plots we can identify the rate of order of reaction, whether it is in the zero order, first order, or second order reaction. So from this, and next of these are some of the examples for off order reactions, and the next topic is 5.10 significance of integrated rate expression. This is nothing but the importance of integrated rate expressions. So here the rate gives some of what are the importance. 1, 2, 3 points are there. First point is rate gives a straight line. Uh, it gives a straight line where rate is the rate of reaction or rate constant. It gives the straight line for zero order integrated expression and not used for first and second order expression that indicates the reaction follows zero order reaction. For example, in single reaction there is three molecules where first occur present zero order reaction, where further the integrated expression helps to decide whether the reaction taking place in the first order, second order, or third order of the reaction. From this integration, we can help to decide whether the reaction is in the first order, zero order, or second order reaction. And from the next topic is experimental determination of total order of reaction. You are going to identify the total order of the reaction. Here, the reaction of this, we are going to identify the total order of this reaction. So here we are taking this one. This one is in NH2CH2COH. It is a glycine uh, with what we are taken. We are taken chloramine T. This cat is nothing but the chloramine T in the presence of HCl and ruthenium. The product formed is CH3CHO. It's nothing but acetaldehyde plus ammonia and sodium chloride and ruthenium 3 RU3. So this is the reaction. We are going to determine the total order of reaction for this example. For to identify the total order of this reaction, here the rate of concentration of chloramine T, we are at different time we are going to plot against x of log into a by a minus x versus time. This is the time for whether the disappearance of this chloramine T follows say this zero order or first order reaction. So this is the plot where this the rate constant uh, from this example we are going to identify here this plot log a by a minus a versus t gives the good straight line which indicates the order of chloramine T where it follows first order reaction. So the graph what we have got, it is straight, so it follows first order reaction. Find order of reaction with glycine. In the next plot is to identify the order of reaction of the glycine. So here we are going to keep the concentration of the chloramine T, HCl and ruthenium constant, and we are going to change the concentration of glycine. So the reaction rate we are going to identify of the glycine. This is the plot for the glycine, where the rate of reaction or rate constant we have got for this is, for the glycine is 1.5. This from the calculated. So for example, we are taking here, if the slope is 1.5, how we are going to calculate the slope here? We are going to calculate the slope by like this: a by b. If you take this one as a and this one as b and this one as c, a by b, b by c. So you will get the value of slope. Slope here, the value of slope is, for example, 1.5 of the rate constant of glycine. This is the 1.5 is the rate constant of glycine. So in the next, from this plot we have got that the rate constant of glycine. So in the next step we are going to find the order of HCl while keeping chloramine T, ruthenium and glycine as constant. By varying the concentration of HCl, here we are going to identify the rate of reaction or rate constant of HCl. So this is the plot by varying log concentration. Here we have got the plot, and from this plot how we are going to calculate the slope here. For this we are going to calculate the slope like this. For example, see A and B, this one and C. It can be written as A by B divided by B to C. So we'll get the value. It is in the negative side. We will get the value of, for example, we have got the value -1. This is the rate constant of HCl with uh, keeping other molecules as constant. So further in the next step, we are going to identify the rate constant of ruthenium with keeping the chloramine T, glycine and HCl as constant. So this is the plot what we have got. This is the plot. Here we are going to identify the rate constant of ruthenium 3. So here this, where for example the concentration of this by calculation it will be in the positive, it may be 2. See, for example, they are given RU3 is 2. So for what is the topic here? What we are told to experimentally determine the total order of the reaction. For individually, I have identified the order of the reaction for each molecule which is taking place in this reaction. So independently, we have find the each order of the reaction. So we need to identify the total order of the reaction. So to calculate the total order of the reaction, here this is the rate of reaction is given by, see, this for the first order here for glycine. What is the rate of reaction for glycine? What is the rate of reaction taking place? It will be around, from the slope we have got 1. This is the rate constant or rate of reaction for the glycine. So that is what we are taken here. This is the 1 for to identify the total order of the reaction. 1 plus 1 plus 1.5 is the total order of the reaction of Which one? Chloramine T. From this slope. And -1 is the total order of the reaction of HCl, which is in negative -1, plus 2 is the rate of order of reaction of lithium 3. So we are going to get the total order reaction by adding how much you will get. 1 plus 1.5 minus 1 plus 2 gives total order 2.5. This is the total order of the reaction. By calculating independently, we are going to add all. So we are going to get the order of the reaction is 2.5. So it is in the second order. And what are the significance of next topic is significance of experimental determination of the rate. What are the importance of determining the rate experimentally? What are the importance? We have to this the by order of reaction explains the effect of concentration of the reactant of the rate reaction. This is the importance means of the determination of the what is the important of determining the rate of the reaction. That is you have to write what are the important. So here order of reaction explains the effect of concentration of the reactant to the rate of reaction. So order of reaction mainly depends on the concentration of the reactants what we are taking. By varying the concentration, the order of reaction also varies. So that is what they are explained in the first point. And second is order of reaction is experimental quantity and dependent with experimental condition. It also depends on the quantity and the condition, at what condition we are going to conduct the reaction. So that depends on the order of the reaction. And further, the determination of order of reaction with respect to each reactant species helps the stepwise mechanism to know to we can also determine the stepwise mechanism for the unknown reaction. Whatever the unknown reaction taking place, we can identify the stepwise mechanism. These are the important significance of this experimental determination of the rate. Further, some of the problems are there. For example, same what I explained in the derivation, you are going to apply this same. This is very much important in this. See, this tabular column you should be knowing for that. For the rate or order of first zero order, first order, and second order, and their half life and the linear plot. This table is important to read. And the first problem is to determine the dihydrogen peroxide of the concentration of 0.22 molar rate of decomposition is 1.3 into 10 to the power of -4 with mole per liter per second. What is the value of K? You are going to identify the first order reaction. You are going to identify the value of K, rate of reaction. So for rate equation of first order reaction, what is the equation? We are going to K into this reactant. What N2O5 dinitrogen peroxide is the reactant giving to the product. So K into N2O5, where it can also be written as K is equal to this K comes on left hand side, K is equal to R by N2O5. Further, it can be written as K into where R value is nothing but 1.3. This is the molar. So 1.3 into 10 to the power of -4 divided by the given concentration of the reactant 0.22. This gives the rate of first order reaction 5.91 into 10 to the power of -4 seconds inwards per second. This is nothing but second minus two, power minus 1 is nothing but the per second. So this is the first problem. If you go through this, you will get the idea. In the second problem, you are going to identify the first order reaction is completed in 20% in 10 minutes. This one, where the specific rate constant of the reaction, you are going to identify the specific rate constant. What is the specific rate constant to complete the 20% of the reaction, and the time taken for the completion of to 75%. The first order of the completion is 20% in 10 minutes. You should calculate the specific rate constant and the reaction to complete the 75%. The reaction is completed only 20% in 10 minutes. So the equation for the first order reaction here is equal to 2.303. This formula should be you should keep in memory, otherwise it's very difficult. 2.303 divided by t log of a by a minus x. This one,
Excuse me, sir. Screen share ಆಗ್ತಿಲ್ಲ
see,
sir.
this one is derived from this previous.
Hello.
See, at first order we have derived this equation. K1 is equal to 2.303 by t log of a into a minus x. This is the equation what we have taken in that problem for first order reaction display. So yeah, they themselves in the question they have asked in the first order reaction. So we are taking this equation k is equal to 2.303 by t log of a into a bar a minus x. So substituting the values the given 2.303 in t is minutes. How much minutes the reaction taking place? 10 minutes. So 10 into log of 100. The initial concentration of the reactant will be 100, where the concentration completed x is the product formed. So 20% of the product has been formed already. So 100 minus 20, the remaining is 80%. The reaction should be completed. So 100 minus 20, x is nothing but the see, this x is nothing but the product formed. So we are going to take it as 20. After calculating, we will get 2.3, 2.32, 2.232 into 10 to the power of minus 2 per minute. For completion of 70%, 75% of reaction, here we are going to put 2. Same for first order reaction, we are going to take 2.303 divided by k log into a bar a minus x. 2.303. So k, what we have got? The rate constant. We are going to take this k 2.232 into 10 to the power of minus 2 log of 100. 100 is the percentage of completion of total reaction. So 100 divided by the reaction should be completed up to 75%. They have asked for the what is the time taken. So for completion of 75% means you are taking x as 75. So this is the question by further calculation. We are going to the time taken for the completion of 75% reaction is 62.12 minutes. So I think you have got some idea. So here in the this one the third problem I will explain further. You should practice, otherwise it will be difficult. Here we are taking which one gaseous reactions in our y nitrogen dioxide, carbon monoxide, gives nitrogen oxide, carbon dioxide. So for different rate, to calculate the rate K into these two reactants K into NO2 of M of CON of N. These are the initial concentration of M. M is the initial concentration of these reactants. So, for example, the initial concentration of this is 0.050, 0.080. These are the three experiments where these are the initial concentration of the NO2 and these are the initial concentration of carbon monoxide here. So here are these are the questions what they asked for. We should identify the order with respect to nitrogen dioxide. So first one, we are going to identify the rate constant of this reaction, and also with the CO also we should identify the rate constant. Both the rate constant you are going to identify, and overall order is total order is nothing but the individual order what you identify. You are going to add that one so that you will get the total order of that reaction. And raw later rate law of expression you are going to calculate for that in the next. In the first step, with keeping order of the reaction with the nitrogen dioxide, here you are going to calculate by keeping carbon monoxide constant. So rate 2 by rate 1. This is the, here some question marks are there, you should take down. NO2 of 2 divided by NO2 of 1. This one above is the M is the concentration. See here. This box should be removed. There is some typing errors. So this M is the initial concentration of the reactant A. If you take this one as the reactant A and this one carbon monoxide as the reactant B, here this is the initial concentration of the reactant A. M is the, so by rate 2 by rate 1 is the what the initial rate here 0.080 what they are given divided by this one here in between it should come. Here some typing errors are there. Divided by 0.080 divided by 0.0050, and here also the initial concentration 0.40, this one divided by 0.10, we'll get this value. M is equal to 2. This is the rate constant for with respect to nitrogen dioxide. So further we are going to calculate for the carbon monoxide how much rate 3 divided by rate 1 by keeping nitrogen dioxide as the constant. We are going to calculate the carbon monoxide. This is the carbon monoxide of the reaction rate 3 with N is the this N. N is the initial concentration of that CO divided by CO. We'll get here also. See here divide should come here and here also. There is no question mark for this. These question marks are typo errors. So 0.0050 divided by 0.0050. This is nothing but the What the rate 3 by rate 2? This one. Rate 3 is 0.0050, and first one divided by rate 1 is also 0.0050. This is what we have taken here. And further, this side on the right hand side, initial concentration of carbon monoxide 0.20 here divided by 0.10. That is the initial concentration at experimental one. So you will get the n is equal to 0. This is the rate constant of the reaction of carbon monoxide. So we have got two rate of reaction. So we are going to find the total order reaction is 0 plus 2. What we are going to get? We are going to get 2. The reaction is in the 2 here. This n is equal to 0. This is the order of reaction with respect to carbon monoxide. For nitrogen dioxide, what you have got? M is equal to 2. So if you want to get the total order of the reaction, you need to add the M both. So M is equal to 2 plus N is equal to 0. If you add 2 plus 0, it is 2. So the total order of this reaction is in the second order. So this is the 2 means it is in the second order reaction. This is the problem. So same as this, you solve for fourth one and fifth. We'll be going for the next unit. You go through the summary, you will get the same what I have explained. And in the unit 6, we are going to discuss about the parallel reaction, consecutive reaction, reversible reaction. We are going to identify the kinetic equation for parallel reaction, for consecutive reaction, reversible reaction, and significance is nothing but the importance of kinetic study for this reaction. What are the importance you are going to study in this unit? Here chemical reaction is the deals with the rate of chemical process. So it generally deals with the chemical process, and further in this study the kinetic of chemical reaction is usually carried out with one or both two different methods. Here it is studied, and this by analysis of the sequence elementary steps giving rise to overall reaction. This is the reaction mechanism, and the next one is the determination of absolute rate of reaction or the individual elementary. You are going to determine the rate of reaction here also. Here the next topic is complex reaction. Here most of the reaction of the complex is nature, which involves more than one reaction step. So the reaction step will be multiple steps. So this is known as complex reaction. Here there are four different types of reaction. One is side reaction or parallel reaction, reversible reaction, consecutive reaction, and chain reaction. These are the four different types of reaction which is taking place. And here we are going to study parallel reaction, reversible reaction, and consecutive reaction. Uh, First, in the parallel reaction, when a reactant A, this one, when a reactant A give rise to more than one product, this is known as the parallel reaction when forming the product B and C. So, for example, if you take, let us consider the A gives rise to B and A also gives rise to C. Both the product B and C are formed, and this is the parallel reaction. Here, for forming the product B, the rate of reaction is K1, and forming the product C, the rate of reaction is K2. Further, it can be written as, to identify the rate formation of B, how much the rate formation of B is formed. So dy by dt is equal to K1. This is the rate const of formation of B, K1 into A minus X. This for the formation of B. And for the formation of C also same. Dy by what you have given. See in the next, dz by dt K2 into A minus X. K2 is nothing but the formation of rate constant for the formation of product C. So here the rate formation of the constant of B and C can be given as dx by dt, the formation of dy by dt into dz by dt. So dy by dt is nothing but k1 into a minus x from the previous reaction what we have got here, plus k2 into a minus x for this one k2 into a minus x dz by dt we are going to value. Further dx, on taking a minus x common, taking on the left hand side, we can write it as dx by a minus x into k1 plus k2 into dt. This is the equation 2. By integrating, we'll get ln of minus ln of a minus x. For this, integrating this equation 2, we'll get minus ln of a minus x, k1 in plus k2 into t plus constant. So we are going to keep time 0 and the concentration x is 0. We'll get when this t becomes 0 and x becomes 0, totally the value what we'll get, constant is equal to minus ln of a. See this, so x will become 0 and this t will be 0 if you take from this equation. So further we are going to integrate here. This is minus ln, it is about minus ln of a minus x is equal to k1 plus k2 into t minus ln of a, or it can also be written as, we're taking this ln of a minus x on the right hand side, it can be written as ln of a by a minus x is equal to k1 plus k2 into t. So further, by calculating, we can write here k1 plus k2, we're taking t on the right hand side, 1 by t. Yeah, this t on left hand side we can be written as k1 plus k2 is equal to 1 by t ln of a by a minus x. This is equation 4. Or it can also be written as k1 is equal to 1 by t ln of a minus x. Where calculating for k1 and k2 initial concentration of the reactant by ln of a by a minus x with respect to t. This is the slope what we will get for K1 plus K2. Slope we are going to calculate A by B into C. A by B by divided by so in the next we are going to identify the rate of formation of product B and the rate of formation of the product C. From this K1 into A minus X, what we have got, this is the rate constant in the previous year. Yes, here. This one K1 into A minus X, this is the rate of formation of the product B, this product, and the rate of formation of the product C is the K2 into A minus X. This one we have taken here. So dividing, we'll get K1 by K2, where this is the big, here two different Ks are there, you don't get confused, where big alphabetical K represent the experimental quantity, how much the quantity is formed, and small k, K1 and K2, this one they represent the rate constant or rate of reaction where the reaction is formed. K2 is big K, it is the experimental quantity. So to know the quantity, you are going to amount of B product divided by amount of C, you are going to get the total product, how much the reaction taking place. So from the above reaction here, the rate constant can be determined here for the total rate for K1 is equal to K1 plus K2. So K2 is equal to K1 by K2. K1 is the rate constant of product B and K2 is the rate constant of product C. So K1 is equal to amount of K2 into rate constant of product C. So it can be written as K1 here is equal to K2 into amount of K2 plus K2 is this K2 is nothing but the rate constant of product C. Further, by taking K2 common, you can write it as K2 plus 1. So K2 is equal to K1 by K2 plus K1. This is the equation what we have got. And further keeping K1 as constant and K2 we are going to calculate here. K1 is equal to K1 plus K2, where K1 value, what is the value of K1, what we have got? This is the value of K2, we are going to insert this value K1 plus K2 plus 1. Further, in the next step, we are going to take the insert the value of K1. K1, what is the value of K1? K1 into K2 plus 1 plus K1 divided by K2 plus 1. By taking this in the next K2 plus 1 multiplying into left hand side, we'll get K1 into K2 plus K1, where K1 we are taking here K1 into K1 as a common. If you take K1 as common here, K1 into K2 plus 1. So hence this we will get K1 is equal to K1 and K2 divided by K2 plus 1. This is the rate constant. This K1 represent the small k represent the rate constant of first reactant. K1 is nothing but the rate constant of product B here, and K2, small K2 is the rate constant of product C. Two parallel reactions are taking place. No, that is the rate reaction. And in the next step, these are the examples what we are given. Nitration of phenol when you are taking here. If you take a decomposition of ethanol has been done, chlorination. These are the example for parallel reaction. Three reactions they are taken, and yeah, further it can be ethylene, water has been formed, and acetaldehyde and hydrogen has been formed using this parallel reaction. These are the examples for the parallel reaction. So, in the next concept, you are going. So, what are the important significance of kinetic study of parallel? What are the importance of parallel reaction? There was kinetic study of this reaction indicates whether the reaction is in side reaction or consecutive reaction. Here you should be knowing what is consecutive reaction. Consecutive reaction is nothing but the reaction in which the reactant formed after the reaction as an intermediate, and further the intermediate is converted into the product. So there will be a multi steps. That multi-step reaction is known as the consecutive reaction. So in the next we are going to study the kinetics of reversible reaction. Now we have studied about the parallel reaction. In this we are going to study the kinetics of reversible reaction. Reaction exhibiting the tendency to reverse the reaction. So it is known as reversible reaction. Here hydrogen iodide is converted to hydrogen plus iodide. Further, it is reversible here. So this aroma represent the reversible reaction. Here ammonia is converted into nitrogen plus 3 moles of hydrogen, and it can form reversely also. Ammonia can be formed. So for example, you will take this one reaction A converted into B with forward reaction, which forms the with the rate constant K1, and in the backward reaction, reversible reaction, it will form K2 is the rate constant, rate reaction for this reaction. So how we'll write this expression for this reaction? We are going to write dx by dt K1 of A minus x minus K2 of x. K1 is the rate constant of forward reaction. K2 is the rate constant of backward reaction. A is the initial concentration of the product A. This is the concentration of the initial concentration of A. This small a is represented. And X is the initial concentration of the, oh, sorry, here, see, this X is denoted as the product from A to B, which is converted, the amount of product. The small x is denoted as the amount of product A is converted to the B. How much amount the amount of reactant is converted into product. So further require it can also be denoted rate of forward reaction is equal to rate of backward reaction. This in the reversible reaction. So here keeping excess constant means it will be equal na. Here rate of forward reaction is equal to backward reaction means the conversion of A to B or B to A will be equal. So if dx by dt is 0. When x is in the constant at the equilibrium state, x is in the equilibrium state means forward reaction also is equal to backward reaction, means it is in the equilibrium state. So further it can be written as K1 into A minus X is equal to K2X. If it comes on this reaction, when it comes on the left hand side, minus will get positive. So it can further it can be written as K2 is equal to K1 of A minus X E divided by Xe. This is the equation. By further substituting in the equation 10, what the equation dx by dt is equal to 0. So dx by integrating here k1 axe minus k1 xe into x, where you are multiplying this k1 a minus k1 xe, and in the equation 10 further in dx by dt k1 ax e minus k1 ax is equal to k1 we are taking common here, and further xe minus x by xe. This is the equation 13, while dx by xe minus x, while xe minus x will be taken on the left hand side here, and is equal to k1 into a by xe into dt. This is the equation 14. By integrating both the sides, you will get integral of dx by xe minus x k1 a by xe into integral of dt. So further integrate minus ln of xe minus this one minus x, this k1 a into divided by xe into t plus constant. So when t is 0 and x is 0, both are in equilibrium. So the constant it can be written as whole. This t is 0 means this will become 0, where x is 0, this is xe minus x. So this x will be 0. So further in the constant equals, this constant equals minus ln of xe. This one will take it in this equation. Then minus ln of xe minus x is equal to k1 by xe into t minus ln of xe. So finally what we'll get here from this integration, here this one is k1 or 1 by t. Here this one is k1 and 1 by t. Further xe divided by a ln of xe by x naught xe minus x. Since k1 is equal to a minus xe, from this one is from the rate of this k1 is equal to a minus xe is equal to k2 into xe. So this one is the rate constant of what we have got here. Yes, rate constant of forward reaction. This one k1 and k2 into xe. This is the rate constant of backward reaction, where x is the moles of amount converted into product. So further we are going to write k2 plus k1, the rate of total order reaction. K1 k2 plus k1 is the total order of reaction. So it can be written as k1 a into xe from this equation. Further, while the equation 15 and 16 can be written as, where in the previous, what is the 15th equation? minus ln of xc minus x is equal to k1 a by xc into t to minus ln of xc. So it can be written as 1 by t ln of xc by xc minus x. So plotting the graph xc by xc minus x versus t, we'll get the slope of k1 a to xc. Here the rate constant or reverse, this is the rate constant for forward reaction where a forms to the b, a to b. So for reversible reaction is b to a. So for the formation of the this, yes, reaction can be this for the forward reaction, as it is for the same we can calculate for the backward reaction also, where the reversion can be evaluated. So this for the forward reaction, same for the backward reaction also it can be plotted by plotting the graph ln of x naught xc by xc minus x versus t, where k2 plus k1 from the slope equation 17. Hence, knowing the value of k1 and k2, the total order of the reaction also can be also calculated. Similarly, we can obtain the kinetic equation for then that's what we are forming of reversible reaction. This is for forward reaction. What we have find the rate of constant. So here we are going to identify the reversible reaction. What this the A forms the product B plus C. So for reversible rate constant is K2. So for identifying it, K1 is equal to Xc by T into 2 minus Xc. So ln of A into Xc plus X into A minus Xc by A into Xc minus X, where A is the where small a, the small a denotes the initial concentration of the reactant A. So X is the amount of A converted to B, the amount which it is converted into the product. It is known as X here. So T is the time. In the next, from the K2 can be written as K2 is equal to K1 by A minus Xc divided by Xc square. So for reversible reaction here, see for different reaction here one reactant is taken where forming the two product, and for this here we are taken two reactant forming only one product. For so for this it can be written as K2 is equal to K1 into Xc by this one. This should come here in the numerator divided by Xc. Xc into A square plus Xc into Xc divided by A square into Xc minus X. This should be in the numerator divided by this Xc. This is the equation for reversible reaction type 2. And where in another reversible reaction where A plus B, two reactants are taken forming two products. For this, you are going to write this equation K1 is equal to, it's not much important, but for different reactions, you should be knowing how you are going to calculate. So K1 is equal to Xc by 2AT into A minus Xc into ln of ln of x into a plus 2xc divided by a into xc minus x plus axc, where it can be written k2 is equal to k1. Further a minus xc is just taken common, and where Mn is Xc square divided by Xc square. This is the equation for two reactants and two products have been formed. So next is the next important this important topic is consecutive reactions. Here consecutive reaction is nothing but the reaction form of an intermediate. Here, for example, if you see A is converted into B product and B is B, C, D, E. These are the intermediates further forming the product. So consecutive reaction is nothing but the reactant form from intermediate, and intermediate is converted into the product. So there will be multiple steps. So the multiple steps are known as consecutive reaction. Here is A is converted into B and B is converted into C with the rate constant K1 and K2. So here in the next step, you are going to identify the rate of reaction. Here C naught, here we are taking C naught as the initial concentration of the A. For the A reactant, we are going to take C naught as the initial concentration, and for the B, C here, concentration of A, and for the C1, C2, C3 for ABC, concentration of ABC. So it can be written as C naught is equal to C1, C2, C3 are the initial concentration of ABC. What this ABC? This reactant with intermediates. So from this equation has taken equation 2. Further rate of disappearance of A. At what rate the rate A is converted into intermediate B. So rate of disappearance minus D into D by T of C1. Initial concentration of A, that is known as C1 into rate constant. What will take K1 at the rate of K1. This is the at what rate? This is the K1. Yeah. So K1 into A moles. So further it can be written as K1 into C1. DC1 by C1 is equal to K1 C1 dt. To identify the rate of disappearance of A means it is nothing but the formation of the intermediate B. So rate of disappearance of A is nothing but the formation of B. So it can be written in the equation 3. Further integrating on the both sides for this minus integral of minus dc1 by c1 is equal to k1. This one is k1 and c1 integral of dt. So further there is some typical errors. So further it can be written as ln of minus ln of c1 is equal to k1 into t plus constant. K1 is the rate constant of formation of B into time plus constant. So while you are taking T is equal to 0 and C1 is equal to 0, the time and initial concentration of A to B is 0 means ln minus ln of C0 is equal to constant. So further it can be written as ln into C1 is equal to K1 T minus ln of C0, or it can also be by taking on the left hand side, it can be written as ln c1 is equal to ln c0 of minus k1t. So here it can be written c1 is equal to c0 t to the power of minus kt. Here this one. So from this equation, rate of equation of B is given here. Rate of compilation of B is given by dB by dt of K1 C1 minus K2 C2. The K1 is the initial concentration of formation of A to B. K1 is the rate constant. Sorry, K1 is the rate constant of formation of A to B, and K2 is the rate constant of B to C. So C1 is the initial concentration of A and C2 is the initial concentration of the B. It can also be written in the dC2 by dt, d by dt into C2 is equal to K1 C into C1 K2 C2. Further, it can be denoted as d by dt of C2 plus K2 C2 is equal to K1 C1 by K2 C2 is taken on the left hand side. So further by multiplying with e to the power of K2 t in of yes, whereby multiplying both the sides we will get this equation. uh, Further, this is the equation what we get by multiplying. Further integrating with respect to t, we will get K2 into C2 by integrating this equation. You can write K2 into C2 integral of e to the power of K2 t dt and is equal to by this one. This one is divided by e into e to the power of K2 minus K1 into t is equal to K1 into C naught, where integral of e to the power of K2 minus K1 t by t. Further, it can be seen in the next step plus constant. It can be written as sorry, see here. It can be written as K2 into C2 e to the power of K2t divided by K2, where this right hand side K1 into C naught e to the power of K2 minus K1 into t divided by K2 by minus K1 plus constant, where t and C2 is taken as 0. We'll get the equation when t becomes 0 and C2 becomes 0. We'll get minus K1 C naught divided by K2 minus K1. Hence, the equation can be written as here. This C2 e this C2e to the power of K2t is equal to K1 C naught e to the power of K2 minus K1 into t. This one K2 minus K1 minus this value K2 C2 can be written as K1 C naught divided by K2 minus K1, where further resolving it can be written as C2 power e to k, and we are taking K1 C naught 2 and K2 minus K1 as common. It can be written as E minus, where you will take this K2 minus K1. Let's take a common, so we are written here. Further, it can be written as e to the power of minus K1t minus e to the power of minus K2t from this equation 10. It can also be written where for the we are going to find the intermediate reaction of the product C. So here what is the See, A to B and B to C. We are going to find the rate of reaction for the product C. So for C3, it can be written as C naught minus C1 minus C2. We'll get the value where C3 is equal to C naught. What is the value of C naught? By for C naught, the initial this is for C1 and C naught minus C naught e to the power of minus kt. These values you are going to integrate in this equation. C3 is equal to C naught minus C1 plus C2 minus C2. So C naught is equal to minus C naught e to the power of minus K1t minus K1. This equation is taken from here. C2, what we have got this value for the C2. And further C3 is equal to C naught. This is the bracket. C1 we are taking common. C naught is taken common here, and 1 minus e to the power of minus kt minus this one, what we have taken, minus k to the power of k1 c naught divided by this one k2. This one is k2 minus k1. This one they came below in the denominator. This one is k2 minus k1. So further e minus k1t minus e minus k2t. This is the equation 11. Further from this, knowing the initial concentration of A, B, C, such as C naught, C1, C2, C3, we can calculate the rate constant for the K1, K2 of the formation of the product. So by this, we can identify the rate constant. As you can see, the concentration of A, this is the A peak with respect to time, as the concentration of A is getting decreased here with the time, means the A is converted into the product B. So the concentration of A is decreased with the time, means A is converted into the product B. So as the time, see the B peak for the molecule B, here B molecule increases with formation of B increases with the time, and see see this is the concentration of A with respect to time. As the A is converted into B, the B molecule will increase the concentration, and further it will decrease as the time proceeds. Why? So that B is converted into C. This B molecule is converted into C. So as the time further decreases with time, and B is converted into C. So as the time proceeds, the concentration of C increases and the formation of the product is formed. So the concentration of the C increases with the time. This what they have merged all the reaction of A to B, B to C. This is the plot what we have got. From this, we are going to identify the rate constant. So here. At maximum C2 is known as dC2 by dt. C2 is the concentration of formation of product C. So when it is 0, it can be written as dC2 by dt for the reaction 12. What the reaction it is? For this reaction dC2 by dt is equal to 0 means K1 C0 by K2 minus K1, where minus K1 is e to the power of K1 into T plus K2 e to the power of minus K2 into T. This 0 is equal to 0. Since K1 C0 and K2 are constant, the rate of reaction of are kept constant, and the initial concentration of the A also is kept constant. Then K1 by it will be 0, so it can be written as K1 C0 divided by K2 minus K1 it's not equal to 0. So these are all will become 0. So K1 by K2 is equal to K1 e to the power of K1 minus K2 into T. By integrating ln of K1 by K2 is equal to K1 minus K2 into T. This is the equation what we'll get. And further example, if you take this is what the consecutive reaction from A to B and B to C, C to D, and further it forms the product. Uh, this is the reactive example they are given reactive series as an example here. Here we have taken ethanol forming the rate constant of K1 forming the intermediate CH4 methane, and further plus CHO1 aldehyde is formed, and further the product is this the intermediate where methane and aldehyde and the formation of hydrogen or carbon monoxide is the product form. This is the reactive series what they are given one example, and one more is CH3TO further forming CH3CHO formation of same methane. There are two different reactions here. This one is methane plus carbon monoxide also is formed. And coming to the summary, you go through this summary very small, and this is the end of this unit 6.